Yeah, welcome to this part of the lecture course that deals with molecular dynamics and molecular dynamic simulations. I assume most of you have had a look at the these lecture at the notes and at these pre-recorded sessions. As you all know, so this tutorial now is the purpose of it is that you can ask questions, and you know, don't be afraid in the end to ask any questions, because I'm pretty sure your colleagues, they will have sort of similar questions. So I guess nobody's seeing you, so this is so it's just audio, so it's probably there is a bit less of a barrier, I guess, or maybe even that increases the barrier, I don't know. But so there are no stupid questions or something. So it's also sort of the language I was using is you know, was also a little bit formal. So and the problem is that every lecture probably is using a different notation for the same you know, physical property. So, you know, if you have problems with, let's say, the notation to start with, then please just let me know, so that we can sort out these problems first. So, maybe I should just invite questions. So, has anyone a question now? Okay, so I do have a list of participants. Everyone's microphone is muted, and it seems nobody's raising his or her hand.
Hi, Jochen.
Hi. Who is this? Hi. JC?
Sorry, my name's Jack.
Oh, Jack. Hi.
I'll just ask my question and I'll change my name on Zoom.
Yes.
That's all right. Yeah, I had a question about something that you talk about relatively early on. I think you're discussing the terms. I'm looking at page 5 of the first set of notes, where you go through the Born-Oppenheimer approximation. And you're discussing the terms that are included in the potential energy surface. And my question is, does it not also include the nuclear interaction term?
Yeah, that's always a cause of confusion. Can you actually see, when I advance the slides, can you actually see now the slide with the potential energy surface with the cartoon there? Can you see that?
I actually can't. I can just see terminal.
Oh, you just see a terminal, because I'm currently screen sharing. So you don't see my, what is that? Oh, so sorry. So that's, oh, okay. So it's the wrong source. Sorry for that. I think now you see my slides, right?
Yeah. Now I can see it.
Okay. Now you see the slides. Okay, good. So the question was, where do we have the here? Yeah. So this is the total Hamiltonian in equation 2, and the question was whether the potential energy surface includes the nuclear interaction term, which is this VNN. Yeah, that was the question.
Yep, that's right.
The answer is usually yes, you include that in that potential energy surface, even though there are no interactions including electrons. And the reason for this is that this VNN is just, you know, it's just a constant for a given nuclear configuration. And it's just more practical to include that in the definition of the potential energy surface than, let's say let's say, having it in the let's say, including it as a term in the nuclear Schrödinger equation. So so this is really just you know, you just imagine you have your nuclei everywhere in space, and then you just calculate the Coulomb, the simple Coulomb interaction between all the nuclei with a given charge of the nuclei. And this is just a constant for a given point on that potential energy surface, and then you just add this to the to that potential energy surface.
Okay. Yeah, I thought it was included. It's just this sentence on page 5 where it discusses the terms that are included and it's not mentioned, but yeah, that's fine. I think it might.
Oh, I didn't mention that. I left it out. Yeah, I left it out. Okay, that's a good point. So yeah, thanks for letting me know. I sort of had to change the you know, the handout from, let's say, you know, from the normal handout to sort of some presentation suitable handout, and then I probably left that out. So include the VNN. Yeah, I will change that. Okay, thank you.
Thanks.
Are there any other questions? On the Born-Oppenheimer approximation. Don't be shy. So this is the so I assume you're doing this course voluntarily because most of you are probably PhD students. So it's really, so this really serves as an opportunity to sort of, you know, discuss any, you know, scientific or philosophical aspects, let's say, of the Born-Oppenheimer approximation, which, you know, I mean, you know, whenever you do any calculation, chances are, unless you do non-adiabatic dynamics, chances are that you really use that approximation or work within that approximation, which not always holds. You know, I mean, as soon as you do a normal electronic structure calculation with quantum espresso, Gaussian, or whatever, you know, you assume usually the validity of that Born-Oppenheimer approximation. Yeah. Okay, so are there any other questions for, let's say, the other two parts, which is where we moved from the nuclear to the classical description of nuclear motion? No?
I think someone let you know there's a question.
Okay. Yeah, no, there are two. Or maybe that was a mistake. Yeah. What's the? Is there anyone who has a question?
Someone asked the question in the chat.
Is this Victor speaking?
I mean, Qiyuan asked the question in the chat. Maybe you can have a look.
Oh, in the
yeah.
Do we have the chat box somewhere? How can I get the chat box?
Someone can just read it to you if you'd like.
Excuse me?
We can just read it out to you if you'd like.
Yeah, it's probably, I don't know whether I can do screen sharing at the same time, but then it seems that the chat box has disappeared. I just stopped the screen share. Oh, right. And then I can see the chat box. It seems that that's not possible to have screen share and chat box at the same time. Okay, sorry for that. Okay, so that's a question from Ki Yuan. Is this, I hope I pronounce it properly. Can you explain how the chain rule works for equation 10 for the first set of slides? I think you mentioned the chain rule in your video. That's equation 10. If anyone knows how to have a screen share and at the same time the chat box open, That would be useful. That would be equation 10. Okay. So I guess now you, oh no, it's, yeah, okay. I think now you're going to see my presentation again. Just tell me if you don't. Okay, yeah, no, that's okay. So that's actually the mathematical, let's say, derivation of the Born-Oppenheimer approximation. Well, I think since it's all, I mean, since it's all quite sort of a bit mathematical here, it's just important that you realize, you know, what is Hamiltonian, what is a wave function, and on which variables do these things depend. Now, especially here in line 10, you have two operators. One is the nuclear kinetic energy operator, Tn. So that's acting on all the nuclear coordinates, and the electronic kinetic energy operator that's operating on all the electronic coordinates, and the collection of the nuclear coordinates I represent here by a capital R, and the collection of all the electronic coordinates I represent by a small r. Okay, so these are these small r's. Now, if you so therefore, if you, for instance, have a look at the action of that operator on the product of these two wave functions, and you have to know that this electronic wave function, so this would be a wave function that you get, for instance, from, you know, like from Hartree-Fock calculation, or from correlated wave function calculation, or it could be a Kohn-Sham determinant, for instance, right? So these electronic wave function, they depend on the small r's, obviously, on the electronic coordinates. But since they are solved, since the electronic wave function is solved for a given configuration of the nuclei, which I call capital R, this wave function, this electronic wave function, depends parametrically on these nuclear coordinates, and this is why I label, I use a subscript capital R, so to just to show this parametric dependence. So that's important to realize that actually that this operator acting on that wave function, this operator just includes basically the Laplacian of the nuclear coordinates. So this is not just a constant, because this thing depends on all the nuclear coordinates. So that means the action of that nuclear kinetic energy operator on that electronic wave function is not zero, okay, or it's not a constant, it's a function of R. Therefore, we cannot neglect it. So that means that this operator acting on that product, you have to use the chain rule. So it operates on the Tn of psi of R. Oh, by the way, I notice another mistake. And then on the left, you would, okay, so I have to correct that. On the left, you would then have a phi of R, right? So this is not gone, so I have to add this. And so the other second term in the chain rule would be then obviously that this operator acts on the nuclear wave function, because this explicitly depends on capital R. And then on the left of that operator, I should have added the psi R. Okay, so that was a mistake. I have to change that and correct that. So this is the action of that operator on that product. And now the action of the electronic kinetic energy on that product is obviously the psi, the electronic wavefront, depends on all the electronic coordinates. This thing is the operator, the Laplacian in terms of the electronic coordinates. So this one obviously acts on that psi r, so that's not zero. And you again would have to multiply from the left this with the phi r, with the nuclear wave function, which is missing here. But then the second term, since the nuclear wave function here does not depend on the electronic coordinates, this operator acting on the nuclear wave function is 0. Okay, so therefore you don't have this fourth term. Okay, so that's another thing, correct. It's good we went through that equation because it's actually not correct. Is this clear?
Oh yeah, thank you so much.
Okay, good. Yeah. So whenever you you do these derivations, you just have to sort of realize sort of on which variables these functions depend on, and then it's then it's quite obvious. All right. Okay. Here we go. Okay. So any other things? The interpretation, physical interpretation of the Born-Oppenheim approximation, is this clear? I think that's the most important thing, is sort of to understand, that due to that mass difference, you can imagine that the electrons sort of track more or less instantly the nuclear motion. So this is the physical picture of all of that. So if you like, the electrons as the nuclei move or as they vibrate, the electrons will sort of instantly follow that motion, because they are much heavier. I mean, it's the same in astronomy, right? I mean, the sun is also much heavier than the Earth, and when the sun moves, and the sun obviously moves, we just instantly adjust our trajectory to it. So this is fine usually for very heavy elements, compared to the electron. Obviously, electron is a factor of 1,800 light, and then the lightest nucleus, which is the hydrogen atom. So for the hydrogen already, there are small sort of deficiencies in that theory, obviously. So, but usually it's a very good approximation for molecules.
Hi, Jochen. You also mentioned that it's the approximation breaks down, and one of the conditions you mentioned is when the electronic states are degenerate or nearly degenerate. Would you be able to just explain a bit more about why that is?
Yeah. So that's a good question. So so that was our first approximation here. Where, I mean, this expansion here is still exact. So this is you're fine here, and here you include these electronic excitations I, and in that Schrödinger equation, well, in the Born-Oppenheim approximation, we neglect all the terms where you have electronic excitations, and that's usually okay because let's say if you in most, let's say, materials, the first excited electronic state is let's say in the order of maybe an eV or something, higher than the ground state. And as the electrons and nuclei move in time, the probability that the system transits from the electronic ground state to the let's say first excited state is usually very small. So, and this probability you can calculate. So we will not cover that in that course. It has to do with non-adiabatic coupling matrix elements that you have to, that one can calculate. And so these couplings, these couplings between electronic states they tend to decrease linearly with the energy spacing between the electronic surfaces. So, and these coupling matrix elements are proportional to the probability to transit to other electronic states. And that decreases more or less linearly with the energy gap. But for, you know, for more rigorous sort of discussion, I would have to expand a little bit more on this. So so you can of course not make this approximation, and what turns out is that you know, this approximation is good as soon as the energy levels are let's say well separated. Obviously, when you do photochemistry and the photon absorbs, let's say, in the UV-Vis that has maybe 1.5 or 2 eV, then obviously due to that external perturbation, you excite the system in an electronically excited state. And then the system will relax due to several mechanisms, like for instance internal conversion. And then obviously, I mean, for this kind of scenario, this Born-Oppenheimer approximation is no longer valid, because the dynamics in time involves the nuclear as well as the electronic dynamics between the different potential energy surfaces. But this is a very interesting topic, but I feel it would go a little bit sort of maybe beyond the content of this course, but I think would probably be good actually to talk a little bit more about that, because that's obviously important for lots of things in biology. For, you know, that's the mechanism of vision, photosynthesis. I mean, it's you know, solar to fuel conversion, all these things you need for all these things. The Born-Oppenheimer approximation is not good enough. I don't know, was this sort of satisfactory answer?
Yeah, it's interesting. Thanks.
Yeah. Right. So okay, there was a couple of good questions. Anything else that we should clarify regarding Born-Oppenheimer approximation? No. I mean, what I would like to say, and I also said this in the recordings, is that, you know, it's, you know, theoretically, it's not obvious that this is actually a good approximation. Especially, it's not obvious that actually that equation 11 holds here. I mean, we have this, obviously we have this division by the mass of the particles here in the kinetic energy operator. But, you know, I mean, you also have a Laplacian here acting on this electronic wave function, Laplace in terms of the electrons, Laplace in terms of the nuclei. And so what you would also assume is that the Laplacian of the electronic wave function with respect to these nuclear coordinates is smaller than the one for the electrons, which is also typically the case. But you know, it's not intuitively obvious that this is the case. But it's, as I said in the recording, is that if you it's the comparison to experiment that sort of tells you that this is actually a very good approximation. But you know, showing it mathematically is not so easy, or probably hasn't been really established, I think. Anyways, so this is if nobody else has questions on this, then I close that set of slides, and I continue with the classical motion. Okay, so that's the classical motion. So I mean, it's sort of a very sort of I would say at least for me, it's a logic sort of order of a hierarchy of approximations. I mean, you start from the full thing, introduce a Oppenheimer approximation that gives the potential energy surface, and then you want to go from the quantum to the classical description of nuclear motion. Are there any questions? I mean, this is also something that you probably 99% of you, unless you work in the area of quantum dynamics, are doing, you know. I mean, your material, if you do material simulation, you will probably treat all the nuclei classically. Again, this is probably okay. I mean, we know it's okay if, you know, if your nuclei are heavy and if your temperature is somewhere close to room temperature, and you're not sort of trying to do something at, you know, very low sort of temperatures of 10 Kelvin or something like this. I mean, what you have to be careful there, though, is when you look at vibrations. Typically, I mean, the classical approximation is fine as soon as you know the thermal energy is larger than your vibrational energy, and that's actually usually not the case. I think that turnover at room temperature is about 300 or 400 reciprocal centimeters. So even at room temperature, your sort of high frequency vibrations, like the sort of CC stretch vibrations and all these things, should actually be treated quantum mechanically. But you know, depending on the problem you're trying to solve, this is not always cannot always be done, and then there are also sort of some corrections that one could use. As I said, also there are also molecular dynamic schemes that allow you to treat the nuclear motion sort of quantum mechanically, but using classical FD simulation. These are these path integral methods. I'm not sure whether any one of you is using those. So that's also kind of sort of specialized field that's becoming sort of more popular with increasing computer power. It's possible to do that. Okay, I don't know whether you have seen these things before. Going from quantum to classical, it usually involves taking the limit of h bar goes to 0 at a certain point, as we have done here in step 3. I mean, it's actually quite nice to see this correspondence principle, and that you arrive at an equation that's sort of isomorph to a classical equation of motion. And to identify this correspondence between, let's say, the phase of the wave function S and the classical action, and the gradient of the phase and the classical momentum, let's say. Right, and the remainder of that part of the course, we're basically dealing with just with Newton's equation of motion for the nuclear motion. Are there any questions? Is it all clear?
Hiya.
Yes.
Yeah, I'm just wondering, why do you take the h bar limit to 0? Why is that?
Well, this is the usual step that you do when you want to derive classical equations of motion from quantum mechanics. Why I do that is because I would like to derive a classical equation of motion, and that requires me to take this limit. That's the, I don't know whether this is a satisfactory answer, but you know, I mean, you know, just it seems to be the case that, you know, by taking that limit, you just arrive at the classical equations of motion. And so obviously this is not the case. H bar is not 0. And therefore also the classical equations of motions are, you know, not true and correct, but an approximation. But again, in certain limits, this classical motion is pretty good. So it's as I said, it's good at very high temperatures and at large nuclear masses. Then the fact that you take H bar to 0 doesn't matter that much.
Okay.
Is this yeah, it's just, you know, for technical reason, I just want to derive something classical from quantum, and that's a usual step that you always see. If you don't do that, you cannot derive the classical equations of motion. Is this okay? Letizia is unmuted.
Hi.
Hi.
Yeah. Well, I think it's because I'm maybe not part of the area, so I'm still a bit confused as to like what does it mean in practice to approximate the motion classically? Like what are we ignoring here?
Okay. Yeah, no, that's a good question. So it's okay. So you know, when we start from the very first principles, we consider the electrons and the nuclei, and then we write the wave function for the electrons and the nuclei, and they contain all the coordinates.
Mm-hmm.
And then we make sort of this product ansatz where we say the total wave function, the mixed wave function, electrons, nuclei, we write it as a product of an electronic wave function and the nuclear wave function. Yeah, so that's what we do at the beginning.
Mm-hmm.
And you know, a nuclear wave function is pretty much like an electron wave function. Even if you just imagine a single particle like a hydrogen, a proton, like the nucleus of a hydrogen atom, you know, should be described by a wave function. That means that it has a probability. I mean, the wave function, there is a probability at each point in space. There's a probability that you meet this proton or this nucleus of the hydrogen atom. And that probability is proportional to phi squared. Okay, if we call this thing phi, so that's the wave function, right? So it's a continuous function in space, and at each point in space, it has a value, and the value square is equal to the probability to meet that proton at that point in space. Yeah. So so this is a wave function basically. So it's not it's not a point particle in this sense that where the probability to meet it at a given point in space is either 1 or 0, like in the classical case. It's really a sort of a continuous function in space. Yeah, that's a wave function. Yeah. So that's the meaning of a wave function. Whereas a classical object would just be like you know, a point object that basically at a given so it follows a given classical trajectory, and so this particle is at a given point in space. It's either there or it's not, but there's no probability associated with that event.
Okay. Yeah,
Okay.
that makes sense. Thank you.
Yeah. All right.
Sorry, that's kind of related to the question that was asked before, right? Because if you take H bar going to 0, then you can imagine like the Heisenberg uncertainty principle not having this lower limit. Instead, it goes down to 0.
Yeah, that's all related to it. Then none of these things anymore hold anymore in the classical world, obviously. Yeah, that's right. Yeah. So this is why classical description of the world is not correct in the how should I say, so not strictly correct, right? But as I said, in certain limits, it's it's perfectly valid. There is no difference between classical and quantum. Like our planets are very heavy. You wouldn't think of describing the trajectory of the Earth quantum mechanically. At least I wouldn't. And that's good because the quantum mechanics is usually for the small things and that are very light, and planets are very heavy. So to calculate their trajectory, it's usually sufficient to use Newton's equation of motion to do that. Okay. Any other questions? No. Okay. Okay. Now that's nice. I get a couple of good questions. That's very good. So let's now look at this third set of slides. Basically, the third set of slides deals with sort of practical algorithms that people have invented to solve this sort of innocent looking Newton's equation of motion. So I'm going to close this now and try to share that. Share screen. All right. Molecular dynamics, the title of that part of that lecture. Yes, are there any sort of burning questions with regard to MD simulation?
Would you be able to explain what the difference actually is between DFT MD and ab initio MD?
Okay. Between DFT and so this is actually the content of the next, basically of this week's recordings. But I can already say something about it. Obviously, of course. Now I think so that's very good questions because it sort of connects probably to all the previous lectures that you've heard so far. So in the previous lectures that you heard so far is that you did static calculations, static electronic structure calculation. With static, I mean, you put the nuclei, basically the atoms of your material or the atoms of your molecule, you put them somewhere in space, yeah, typically at the, let's say, equilibrium configuration, yeah, where the molecule or the material is happy. And then you fix them in space and you don't care about them anymore. And these nuclei, they of course then create this external potential in DFT calculations, and then you solve, try to solve the electronic Schrödinger equation for this nuclear configuration. And then I mean, I don't know, you probably have quickly heard about the first thing how you would do that is Hartree-Fock calculation. And then, but then in the 60s, these DFT calculations have been introduced, which looks at, as you now know very well, which looks at the density rather than the wave function as the central variable. for optimization. And then, so you do then a DFT calculation, meaning you solve the Conjam DFT equations for this particular nuclear configuration, okay? And that gives you then the Conjam orbitals, and that gives you then the approximation to the true electronic ground state energy. So that would be the potential energy, right? That you would use in the potential energy surface. And that is the energy for just this one nuclear configuration. Yeah. Now in density in ab initio molecular dynamics, you are interested in how then these nuclei move from one place to the other, in time, solving Newton's equation of motion. So in order to do that, you see that in the in that equation 1 here. In order to do that, you not only need the DFT energy of that system, but you also need the DFT force, the force that acts on each nucleus. And this force then you use in Newton's equation to propagate the nuclear dynamics, right? Now, we will also say much more about this in the next set of slides, is that these Conjam calculations, they not only can use them to calculate the ground state energy, but you also can use them to calculate the force acting on the nucleus. So that's the difference. So the DFT calculation usually is just a static thing. So you just do that for one single nuclear configuration. If you do ab initio MD, or density functional theory MD, then you also have to calculate the force and then propagate the nuclei in time. So this is what I mean here in that. And do I give this here in that? Here, yeah. Are you still with me? I think it was check, right? Check.
Sorry, I just broke up for a little bit there. I didn't hear what you said.
Okay, so could you hear what I was saying? Trying to explain the difference between density function theory and
I heard your explanation.
And DFT MD, yeah.
Yeah.
So I think probably the equation 2 is probably the best to illustrate this. So so this is just a time series of nuclear positions, right? As the atoms move in time. So this is what you're obviously trying to obtain when you solve Newton's equation of motion. So you basically step sort of you change the nuclear positions in time, whereas this DFT calculation that you had before in these previous talks, you would typically just look at one single nuclear configuration, let's say R at T0, yeah, and then do an electronic structure on that. So now in the Born-Oppenheim MD, you also do this, but then you also calculate the force at that configuration. And then you solve Newton's equation of motion, then you create the next nuclear configuration of the molecule, which is then different. So the nuclei have moved. And then again here, you again solve the DFT Conjam equations to again obtain the Conjam energy and the forces acting on the nuclei at that given configuration. You again use this, solve the Newton's equation of motion for the next time step, and then you move your nuclei to that next position, and then you again solve the Conjam density function theory equations for this new positions and the force and so on and so forth. So the DFT-MD is just a sequence of solving the Conjam equations and the nuclear forces for a series of nuclear configurations. Is this?
Yeah, maybe I missed it, but so in the DFT MD,
yeah.
how do you, if you're not working out the forces, how do you know how the nuclei should be moved?
Okay, so that's a good question. That's what these algorithms, the time stepping algorithms, are good for. Let's assume here. Okay, so do you see this slide, velocity Verlet algorithm?
Yeah, I do.
Right, so that's a good question. So, okay, so this is the time stepping algorithm that is usually implemented in most, let's say, electronic structure packages like quantum espresso, whatever you're using, CP2K or Gaussian, I guess, can also do that. So okay, so how does this work? So imagine we are now at time t, and our nuclei of our molecule of material are at a given set of positions that we call Ri, yeah, at given t. Now, at that position, you do a conjunct calculation. The conjunct calculation gives you the energy, the ground state energy, the point on our potential energy surface, and it also gives you the force acting on each nucleus of your material or of your molecule. Yeah. What you also have at that time is the velocity on each nucleus, yeah, which is the r dot. You know, when you solve Newton's equation of motion, you need to specify initial conditions. So you need first to specify where are my nuclei at the initial time and how fast are they, right? So it's a second order differential equation. So you need to give these two initial conditions, yeah? So this is the initial condition R, and the second initial condition is the R dot. So that's just specified by the user. Okay, so that's not, you don't have this, so that's just specified by the user. Now you do this DFT calculation to get the ground state energy and the force on each nucleus, and then you use this in that equation. And since you have this and this as an initial condition, this you get from DFT calculations. You can then calculate using this expression on the right-hand side. You can then calculate the position of your nuclei in the next, after the next time step, after the next time increment delta t. So then you know where are my nuclei at t plus delta t, given I started at time t. Is this clear?
Yeah, I think that makes sense.
Yeah, that makes sense. And then here the last equation, because if you do this again, you then need the velocities also at time t plus delta t, and you need then also the forces again at t plus delta t. Now, how do you do this? Well, according to the velocity Verlet, the velocities then at the next, after the next time increment, is then just given by the velocities that of my nuclei currently at time t. So these are known, and the mean of the forces at time t and t plus delta t divided by 2m. So that's acceleration, right? But the interesting thing is in that algorithm, to calculate the acceleration, you need the forces at the current time and at the time that you're stepping to. But this Fi of t plus delta t, you can calculate because you know the positions, because I know already the positions at t plus delta t. And what I have to do at t plus delta t, I have to do another conjunct calculation to get the, again, the ground state energy at that position and the forces at that position. So then I have this, and once I have this, then I calculate the new velocities at that new position t plus delta t. Yeah, so then I have again so this and that, and then I can continue. I can then calculate the next update t plus 2 delta t and so on and so forth, and that creates then a discrete trajectory of my nuclear positions in time and a discrete trajectory, if you like, of the velocities of my nuclei in time. Okay, so it's just a sequence of DFT calculation that you have to do for each time step. And what you actually need, you don't need the energy, you need the force for the time stepping, because you don't do anything else than solving Newton's equation of motion. But with forces that come from proper, let's say proper from density function theory calculations. Yeah. So if you like, Newton's equation of motion plus density function theory is density function theory based molecular dynamics. So that would be the kind of equation.
Okay. Yeah. Thanks.
Okay. Good. Yeah. No, it's good that you asked that. Okay. Any other questions on that? Yeah, here's just a sort of a list, incomplete list of the types of MD simulations that are sort of common. So, I mean, the most straightforward, the kind of MD simulation is a classical MD simulation. Now, classical here does not refer to the motion of the nuclei, which are always classical. It also refers to, let's say, the fact that the forces that I was just talking about that you need for the time stepping here, they don't come from explicit electronic structure calculations, like, for instance, like DFT or something. No, and they come from a force field. So you describe this potential energy function by a set of empirical functions that are empirical functions of the coordinates. Yeah. So for instance, the easiest one would be just a harmonic oscillator. So we know that the potential energy of a vibration is roughly quadratic, is parabolic. So instead of calculating the ground state energy for different displacements of your nuclei along a given sort of vibrational coordinate, instead of getting that from DFT calculations, you just say, okay, so I just assume that this is a parabolic function. So you can fit then these parabolic functions, for instance, to data that you get from electronic structure calculations. But the advantage is that you have an analytic form of your potential energy surface that's called force field, and you have an analytic form of your forces, of your nuclear forces. So that means this is very quick to calculate. So basically you don't need, so you have almost instantly, without much computation, you have the forces on your nuclei. Whereas if you do, if you use density function theory to get the forces, then obviously each step you have to do one DFT calculation, which of course takes a lot of time to do, as you probably know. The advantage of these classical MD simulations is that you can go to very large systems and to very large time scales, because the computational time that you need for a given time step is very short. So you can probably nowadays can do one time step with classical MD maybe in a micro to a millisecond of a protein, whereas for like let's say 100 molecules of water with DFT MD, it probably takes you half a minute, yeah, to just do one time step. On the other hand, classical MD, I mean, you have empirical force fields, so they're not typically not very accurate, and you cannot do chemical reactions, for instance, whereas with DFT MD you can simulate chemical reactions, for instance. So that's so depending on the problem you have to solve, you either use classical MD for large systems or for long time scales, but then you can't do chemistry, or you can do density function theory based MD. So these are the things that I very briefly mentioned. Other types of molecular dynamics, non-adiabatic molecular dynamics, where you have more than one potential energy surface going beyond the Born-Oppenheim approximation, and path integral molecular dynamics, where you include nuclear quantum effects. Okay, so what I wanted to, maybe I think I have a, where is this animation thing there? Maybe that sort of invites a few more questions. So, share screen. All right, so you can see this, yeah? So this is just an animation that you actually can take from Wikipedia or somewhere. So this is a water molecule. And so this, I just show these normal modes of the water molecule. And so these are these vibrations I was talking about. So this vibrational motion already assumes the Born-Oppenheim approximation. Okay, so you assume there's a potential energy surface, and the molecule in its equilibrium geometry sits at the minimum of that potential energy surface, and in that minimum it sort of vibrates, right? So so these are the normal modes. So in order you could do classical MD simulation of that, and then at each point in time you would need to calculate the Cohen-Sharma equations, get the ground state energy and the forces, and you propagate the molecule in time, then you would get this. Yeah. So these are the different normal modes. There are three normal modes, of course. That's the asymmetric stretch, the symmetric stretch, and the bending motion. Okay. So that's all happening on the ground state potential energy surface in the Born-Oppenheim approximation. Okay, so this is why you don't see any electrons here in that movie. All the electrons, as I said many times, they are in the potential energy surface, and what you see is only classical nuclear motion. Okay, so this molecule has 3 atoms, so it has some 3n minus 6 normal modes. So the other ones are just rotations and translations. Okay. Okay, that's just a single molecule. Now, since this is on materials modeling, of course, I thought I show you sort of something that's related to materials modeling. So this is a molecular dynamic simulation of an interface of iron oxide or hematite with liquid water. And this is an MD simulation, right? So you see the molecules and the atoms, they move in time, and you nicely see the hydrogen bonding between the water molecules and between the oxide and the waters. And these are not sort of static things, right? So the hydrogen bonds get created and get broken. And so this kind of material is important for photoelectrodes and for water splitting and hydrogen generation. So this is an MD simulation of a material, and so this would be an MD simulation of a whole protein where, people are still around. So where actually this is simulation that has been done in my group, where we're trying to understand how gas molecules enter the active site of an enzyme. And so here we did classical MD simulation of oxygen diffusion. So this is an enzyme that actually is very nice. It's producing hydrogen from protons. And the oxygen actually inhibits the enzyme. So you actually want to keep the oxygen out. But so you want to know how the oxygen gets into the active site. So we did MD simulation of that system, and sort of this is the kind of trajectory that you see. So what you see here is how the oxygen molecule diffuses at around 300 Kelvin towards the active site here in the middle of the protein. And so here MD simulation you can use to understand through which paths the oxygen goes towards or diffuses towards the active site. So here you could see that there is a channel that's inside the protein that the molecule uses to access the active site. So this is typically, let's say, hundreds of nanoseconds of simulations. What you see here. So many millions of these time steps. So many million of these T plus delta T steps with forces evaluated from empirical force fields. And then you see that the molecule cannot just quite enter the active site. And then we did some pulling molecular dynamics where you add an additional pulling force to pull the molecule into the active site. From these kind of calculations, you can calculate rates and free energy barriers, and especially you can estimate what is the rate of the attack of that active site by oxygen molecules. Okay, so these are just some illustrations, things where molecular dynamics is actually a very useful tool to understand the function of, let's say, proteins or properties of energy materials. Okay, so time is up. If nobody else has any more questions, then I would like to stop this now. I hope I can do that. If anyone has a very quick question, I'm happy to take it. Anyone? No? Okay. Yeah, so I hope you sort of found this useful, and this lecture slides, these recordings, this week's recordings are mostly focused on this Bonn-Oppenheimer MD. Okay, so this is what we will discuss next Wednesday. So okay, so enjoy these recordings and have a good week. Bye.
Thank you.
Bye-bye.
Thank you.
Thanks a lot.
Thank you.
Thanks.